start नहीं करना. And then CPU will communicate with these three registers. अच्छा यहाँ पे हमारी assumption ये है कि सिर्फ एक character display हम कर सकते हैं. वहाँ पे हमने जो example की थी, it can display multiple characters. ठीक है? अच्छा अब ये जो प्रोग्राम है, so now what's our objective? Program control IO. Start. So there are different types of IO techniques. One is the program control IO, interrupt driven IO, and direct memory access. We will now start explain the program control IO with an example, with a simple example. So in this example, we have an IO device. This IO device is communicating with the keypad, and this is an IO device which is communicating with an LCD. Okay, so there are three registers with the keypad, which is called as SR keypad. SR stands for status register keypad, control register of keypad, and data register. Then status register of LCD, control register of LCD, and data register. So this is the memory map. This is the not memory. Sorry, we call it as IO map. This is the IO map. Each of these registers has a particular address. Now there are some specification. According to specification, when any SR is when any CR is 0, it is an input device. When CR is 1, it is an output device. Okay? When SR is 0, it means not ready. When SR is 1,
ready.
The device is ready. So actually, control register. The direction of the control register will be from where? From microprocessor to the IO device. Because microprocessor is setting the control. So the direction will be from microprocessor to IO device. And what about the status register?
Status register IO device.
From IO device to
processor.
Microprocessor. And now data register. The data register depending upon the type of device. When it's an input device, so the direction will be from the IO device to the microprocessor.
Yes, sir.
And if it's an output device, from microprocessor to the IO device. Okay. So now what's our objective? So our objective is there. Now we have a keypad. Okay. When any of its key is pressed, its ASCII value will be in the DR key.
Yes, sir.
So when any key is pressed, its ASCII value will be in the DR key. And when any value is in DR LCD, that value will be displayed on the LCD. This is our specification. So now we have a keypad, now you have a simple microcontroller, and now you have an LCD. Now we are using program control IO. In a program control IO, microprocessor will continuously check the status of the
keyboard
IO device. Whether it is LCD or whether it is keypad. First we will do configuration. So now what's configuration? So then we will have we want to have a configurable program.
Yes.
Okay. So in configurable program, we define some values. So we say CR LCD equal to, what is the address? CR $2002 SR LCD CR LCD, okay, 3002 SR LCD and DR LCD 3004. Similarly, we have SR key, DR key, and
CR key.
You can equate it now according to their addresses. Okay. Now we want to configure. Okay. Now we have defined some. So we say Then input equal what?
CR equal to 0, 0.
Input equal to 0. Output equal
1,
1. Ready equal
1,
ready is 1. Not ready.
0.
Now this is like we have made some config program.
Yes, sir.
Now we are starting some config. This is startup program. So now we have started org $0000. So actually your program starts from there. $0000. So it's your
Started.
start of the program.
Yes, sir.
Okay, config. We want to. Okay. Now if you want to configure this is a input device. Which value will put in the CR?
CR में
Input.
0,
This should be 0 and this value should be
1.
1. Why 0?
ये input device है.
Input device and 1
Output device.
output device. So now we will move CR key hash input. This value will be replaced with 0. Which addressing mode is this? CR key. It is an address. Direct or absolute addressing mode. ठीक है सारे कंसेप्ट आप याद रखिए. This is direct addressing mode or absolute addressing mode. Then move CR/LCD hash output. Now we have configured it.
Yes, sir.
Configure it. Okay. Now wait of keep it. Now we want to check the status.
Yes,
We
sir.
want to check the status. Move R0. Now we want to move this value, the status register, and move into register R0. $move R0. What is the address of status register? $200. 200.
SR key पे.
SR key. Which addressing mode is this? Register addressing mode. Which addressing mode is this? Absolute. Okay? So that value, when it's 0, what does it imply? Device is not ready.
Register not ready.
A key has not been pressed. When it's 1, it's ready and now a particular key has been pressed. Okay. Move R0 SR key. Okay. Then
Compare R0 with 1.
compare R0 with when it's ready.
तो 1 के साथ. Ready. Yes, sir.
When it's ready,
Yes, sir.
when it's not equal, then wait of
Okay.
it will be in a looping fashion.
Yes, sir.
So in a program control I/O, microprocessor or microcontroller will continuously check the status of the I/O device. When it's not ready, it will be in the loop, and microprocessor or microcontroller will do
Nothing.
nothing.
Yes, sir.
Therefore, this is an inefficient method. When it's ready, it will come out of the loop.
Yes, sir.
When it becomes 1, it means now it's ready, and the particular key that has been pressed, its ASCII value is now in the
Data
here.
register.
Maybe when A is pressed, which value will be pressed here? 65. When B, 66. Okay. Now, when it comes out the loop, it means some key has been pressed. When some key has been pressed, so now we can say
Move DR key.
move R1 DR key. You move that value into some register. Now you want to wait for LCD, because now you need to check the status of the LCD when it's ready or not. So now you can say move R0 SR LCD.
LCD.
Compare R0 with
Ready.
ready. When it's ready, now it's not equal, then what?
लूप चलेगा और else
Wait LCD. When it comes out of that, So the value that has been pressed, where is this now? In which
R1,
register?
R1.
R1. Now we need to move this R1 to which register?
LCD का जो
DR LCD. And that will be, so move. Now DR LCD will be now output. DR
LCD
LCD and
R1.
R1. And when it is done, then it will jump again to jump
Wait keypad.
20. So okay, this type of technique is called as program control I/O. In the program control I/O, whenever microprocessor wants to interact with the device, it will first check the status of the I/O device.
Yes,
And typically the I/O devices are slow.
Yes, sir.
When it's slow, and then microprocessor will looping fashion and it's doing nothing. When it's doing nothing, so I'll explain this with an example. Now let's assume if I ask any student, any attendant to bring me a glass of water.
Glass
Of water. And then I wait for him for 5 minutes and he is not here for 5 minutes. So I'm doing nothing, I'm just in a wait state. What should be an efficient method?
आप आके
I
पढ़ाएं.
ask him to bring me a glass of water and I close the door and I resume the teaching.
Yes, sir.
And when he arrives, he gives me an interrupt. This
Interrupt.
type of technique is called as
Interrupt driven.
interrupt driven I/O. In interrupt driven I/O, microprocessor is not continuously checking the status of the I/O device. Instead, the device informs the microprocessor that now I am ready and available. So now in this type of technique is called as interrupt driven I/O. To support an interrupt driven I/O, so now this is some other mechanism. So how this will look like in this particular architecture? So now you have an architecture. Now you have a microcontroller. Now you have a keypad, and this keypad is connected to IRQ1. IRQ1 is interrupt request 1, and now IR interrupt acknowledge 1 is to this. So this interrupt microprocessor will I acknowledge 1. And now you have an LCD with interrupt request 2, and then it will I acknowledge. So now this status register will not be there here. And now this status register LCD is not an interrupt driven I/O. Why it's not there? Because this status register is directly connected to the IRQ, interrupt request. So the interrupt request is a signal that is generated by the device to the microprocessor that now I want some service from you. I want some service from you. So actually microprocessor is now executing some instructions. So now it is executing some instructions. I1, I2, I3. Let's assume if reaches IK and then IK plus 1. Let's assume microprocessor is executing this instruction. Any instruction, any useful program, and the user press a key. What happens? The keyboard generate an
Interrupt.
When it interrupt, so which interrupt?
IRQ1.
IRQ1. Now microprocessor IRQ1. Now if you look at this instruction, so this instruction has some phases of execution. We have which phases? Instruction fetch stage, then
Instruction
decode
decode.
phase,
Operand fetch.
operand fetch stage, then
Operand.
instruction execute, then operand store fetch, and then next instruction. Let's assume interrupt arrives here. What should we do now? We should complete the current instruction. Which instruction is this?
IK.
IK. So in this case, it's executing the instruction IK, and an interrupt arrives. Microprocessor will complete the current instruction. So there is a time. So when the device makes an interrupt, IRQ, the device makes an interrupt. The interrupt request is a signal that is asserted by the device to the microcontroller that now I want some service. And then after some time, microprocessor acknowledge. And now again, now your I now grant you this address. So what is this latency? This is called as interrupt latency. And maybe यहाँ पे latency कहाँ तक होगी? यहाँ से लेकर अगर इंटरप्ट यहाँ पे होगी तो latency कहाँ तक होगी? Okay, so whenever interrupt arises, microprocessor will complete the current instructions. Microprocessor will complete the current instruction. When current instruction, okay, now let's assume I'm talking to each and individual student in the class. Now let's assume I ask her what's your name, and I ask her what's your name, and I'm talking with her, and somebody interrupts me. I will finish conversation with him. I'll finish conversation to him, and then I will service him, and when I return back, from your execution to start? From the next instruction. From the next instruction. Now, if interrupt arises here, it will store the address of the next instructions on the stack.
Yes, sir.
अच्छा, वो एड्रेस ik plus 1 भी हो सकता है और वो एड्रेस ik plus j भी हो सकता है. क्यों?
लूप के केस.
अगर हम यहाँ पे ये इंस्ट्रक्शन है जंप, अगर जंप की है तो फिर आपने यहाँ पे जंप करना है या यहाँ पे जंप करना है. So it depends upon the type of. So it will what will it do? So when an interrupt arises, it will store the address of the and next instruction to be executed on the stack. It will not only store the address of the next instruction on the stack, but it will also store the content of the status register on the stack. Why status register? Why status register? कि कोई बता सकते हैं, कोई ऐसी सिनेरियो बता सकते हैं कि कोई स्टेटस रजिस्टर को पूछते हैं.
कोई डिवाइस हो, इनपुट डिवाइस भी हो, आउटपुट डिवाइस भी हो.
स्टेटस रजिस्टर माइक्रोप्रोसेसर के स्टेटस का जो स्टेटस रजिस्टर माइक्रो कंट्रोलर में स्टेटस रजिस्टर है N G C and V.
अच्छा सर.
सर इसमें अगर कैरी या कोई भी हमारा बिट,
क्योंकि अगर ये जो इंस्ट्रक्शन है, अगर हम ये कर रहे हैं कंपेयर R0 with #5, so this instruction will update the status registers.
यस सर.
ठीक है, will update this. और यहाँ पे हम कर रहे हैं compare R0 and branch equal to level. Now this is a condition jump instruction. तो ये जो इसको जो कंटेंट्स है इसमें अगर R0 को 5 है और इसके 5 है, what will be the contents of the Z value? Z will be 0. अच्छा, जब वो इंस्ट्रक्शन सब रूटीन पे जाएगी, नेक्स्ट इंस्ट्रक्शन पे जाएगा, तो वहाँ कोई और इंस्ट्रक्शन एग्जीक्यूट होगा, तो फिर वो स्टेटस रजिस्टर को दोबारा चेंज करेगा. तो हमने इस स्टेटस रजिस्टर को स्टोर करना है. Now let's assume if jump is to some other instructions, and that instruction is add R3, R2, R1. अगर इसकी वैल्यू 5 है, इसकी वैल्यू 6 है, what will be the value of Z? Z will be 0 or 1? 0. In this case, Z will be 1. अब जो स्टेटस रजिस्टर को वो कंसिस्टेंट होगा या इनकंसिस्टेंट होगा?
इनकंसिस्टेंट
होगा. तो ये याद रखें. So whenever this is interrupted, so what you push? Push program counter on the stack.
and status register.
Push status register on the stack before jumping to the interruption. And the control will go. So now it's a keyboard. So the control will go to the ISR of keypad. What is ISR? Internet subroutine of keyword. So internet subroutine of keyword. अब जो internet subroutine of keyword कब होगा? वो जो config होगा, this will be only one time. This will be only one time. No problem. अच्छा, अब जो internet subroutine of the keyboard, how will it look like? So it will jump to the internet subroutine of keypad, and the code you will not execute this instruction. So what will it do? Move R1 what?
Here.
The value will be directly transferred here. And then it will return from interrupt. So when ISR keypad, microprocessor is executing this IK. It will push the program counter on the stack and the status register on the stack. Control will be transferred where? Here. The data is now moved in which register? R1. And then return from interrupt. Then control will transfer to which instruction? IK plus 1. IK plus 1 or IK plus J. This, if it will jump on IK plus J, if it is a jump instruction. If it is a following instruction, it will jump here. There can be a backward jump,
Forward.
or a forward jump or a backward jump, depending upon the how the jump address is upper at level or at the lower level. Okay. Now then it will execute. When LCD will generate an interrupt, it will go to the microcontroller. Microcontroller will jump to another subroutine. ISR of what? LCD. Which code will be executed?
Move DR LCD R1.
And this code. So what's the advantage of the interrupt driven IO compared to the?
जहाँ से जरूरत होगी प्रोसेसर उसको सर्व करेगा.
So the advantage of the interrupt driven IO compared to program IO control IO is that microprocessor will not check the status of each individual IO device before servicing its request. Whenever the device is ready, first microprocessor will make a request to the IDOS, I need some service. If device is not ready, it didn't get it. It will say, no, I'm busy, wait. Microprocessor will go some useful task. Will do some useful task. When the useful task, when the device becomes ready, it will inform the microprocessor.
Yes sir.
Okay, now I am ready. Microprocessor will complete the current instruction. It will push the program counter on the stack, the status register on the stack, and then it will jump to the interrupt subroutine. When interrupt subroutine is jumped, it will resume from the location from where the program was interrupted. From where the program was interrupted. When there is another interrupt, each particular interrupt, okay. When microprocessor will jump to ISR keypad, in case of IRQ1 or IRQ2?
IRQ1.
When IRQ1 it will jump to ISR keypad, when it's IRQ2 then it will jump to
LCD.
ISR LCD. So it will not wait. So in interrupt driven IO, microprocessor will not continuously check the status of the IO device. Instead, the device will inform the microprocessor that now I am ready, and now the data needs to be processed, and it will reduce the cutting and microprocessor will reduce.